We're going to be talking about states of matter. Primary focus will be on liquids, solutions, colligative properties, phase diagrams, and phase changes. As you recall a little bit from bonding, there are many types of crystalline solids: atomic, molecular, ionic, metallic, and covalent network solids. Let's review again one more time the properties of different types of solids and the intermolecular forces associated with these solids. So the first type of solids are atomic solids, which are made up of atoms. The units are atoms, and between them, the London dispersion forces keep them together. Because London dispersion forces are rather weak interactions, these type of solids have very low melting points, and they are poor conductors of electricity. And the example of atomic solids are noble gas solids like argon, krypton, etc. The second type of solids are molecular solids, and they are made up of molecules. These molecules could be polar or nonpolar. An example of a polar molecule could be water molecule. A nonpolar molecule could be dry ice, carbon dioxide, or it could even be oxygen, which is solidified, or nitrogen gas, and so on. In between the molecular solids, there could be London dispersion forces, dipole-dipole attractions, or hydrogen bonds. Even molecular solids are poor conductors of electricity, and their melting points vary from low to moderate depending upon what kind of intermolecular force of attraction is between them. An example of molecular solids is dry ice, which is solid carbon dioxide, sugar, table sugar, sucrose, or water. Now, the next type of solids are ionic solids, which are made up of positive and negatively charged ions, which are strongly attracted to each other through electrostatic force of attraction, which is called as the ionic bond or ion-ion interaction. Because this ion-ion interaction is fairly strong, ionic solids are arranged or organized in what is called as crystal lattice. And each unit of ionic compounds is called as a formula unit. And the strength of the ionic bond is determined by lattice energy. And if you recall from intramolecular forces, lattice energy is governed by Coulomb's law, which states that force of attraction between any two charged particles is directly proportional to product of their charges and inversely proportional to the square of the distance between them. Ionic solids are very hard, they are brittle, they have crystal lattice structure, high melting points. These solids are non-conductors in solid state because the ions do not have freedom of movement in solid states, but they are good conductor of electricity as aqueous solutions. Once you dissolve an ionic compound in water, the ions break apart or break free and are able to conduct electricity. And most of the ionic solids are soluble in water. However, there are some that are not, and you can look up the solubility rules to predict which ones are. Some common ionic compounds, ionic solids, are sodium chloride, calcium nitrate, and many other. And here is a picture of sodium chloride lattice. Here is a macro view of salt crystal, and this is calcium chloride dissolved in water. So you can see a bunch of red, which are water molecules, and calcium and chloride ions. Let's move on to the next type of solids, which are covalent network solids. Covalent network solids are large atoms. They are either made up of a bunch of atoms joined together, a bunch of molecules joined together in these macromolecules through covalent bonding. So in covalent network solids, inter and intramolecular bonds are the same, which are covalent bonds. Hence, these are pretty strong force of attraction. That is why covalent network solids are very hard, they have high melting points, they are not soluble in either polar or non-polar solvents, and their conductivity varies. Some examples of covalent network solids are diamond, graphite, silica, germanium, silicon, silicon carbide, and boron, nitride. And Graphite is a conductor, and a little later I'm going to show you an animation to show you different layers of graphite and why graphite is a conductor of electricity while diamond is not. This is a picture of diamond where every carbon atom is attached through sp3 hybridization to 4 other carbon atoms, but in graphite a carbon atom is attached to 3 other carbon atoms through sp2 hybridization, and the s orbital that's not involved in hybridization helps create the intermolecular force through pi bonds, which are weaker bonds, and these layers can slip as you write with graphite or your pencil. The last type of solid is metallic solid. Metallic solid has metallic bonds, which are commonly known as electron C model, and the strength of these bonds is also given by Coulomb's law. The model here is that they're a bunch of positively charged nuclei or the cations, and the valence electrons are not held tightly by these nuclei, so they are roaming about in the space around these positively charged nuclei. Because these electrons have freedom of movement, hence metals are good conductors of electricity. They are malleable, they are ductile, and they have a wide range of melting points, generally fairly low melting points for metals, and they are insoluble in water. An example of metals is any metal that you can think of, like copper, aluminum, iron, etc. And now I'm going to show you an animation that will help you visualize different types of solids. This first animation shows molecular solids. And this molecule here, can you identify this molecule? Yes, this is the water molecule. So this is structure of ice. So you can see the attractive force between them will be hydrogen bonds. And ice as a solid will have structure like this. The next type of solid here is metallic solids, where you can see the free electrons roaming about being attracted by the cations in the middle, yet having freedom of movement. Hence metals are good conductors and malleable and ductile. This is a picture of covalent network solid, a type of covalent network solid which is diamond. Because carbon atoms have no freedom of movement, these are non-conductors, they're not soluble, and they are very hard. This is an example of ionic solid like sodium chloride crystal. This is the 3D view of crystal structure, a lattice structure. Another one to clarify the ionic compounds crystal lattice structure. This one shows how the smaller cations fit in between the negative and ions. This is an animation that shows graphite's layered structure. In between graphite layer are the pi bonds that hold them together. So as you write with a pencil, these pi bonds are broken, and then you can write easily. And that was the animation that hopefully helped you with visualization of different types of solids. Now let's move on to solutions. And guys, you know why everybody goes to chemists with their problems? Because chemists have all the solutions. Okay, so when we say solutions, generally you think of liquids or aqueous. However, as you can see from this table, solutions can be of any type. They can be gas in gas solution, gas in liquid, gas in solid, liquid in liquid, liquid in gas, and so on. So why do solutions form? Solutions have two main components, a solute and a solvent. Solute is what's present in lesser amount, solvent is what's present in larger amount. And solutions form because there are two factors that are working on it. One is the energy of solute-solvent interaction. What kind of bonds are breaking between solute particles? What kind of bonds are breaking between solvent particles? And when ultimately these separated solute and solvent particles come together, what kind of attraction exists between them? This is one factor that decides whether a solution will form. Other factor is called disorder or randomness of a system. Generally, during solution formation, because a very ordered crystal lattice is broken into its ion, the disorder or entropy of the system increases. And these are the two factors that determine whether a solution will form spontaneously or not. Let's look at the case of salt. NaCl, when put in water, this is a common knowledge, when you put salt in water, it dissolves. Now let's look at what kind of bonds are being broken. So between NaCl formula units, what kind of bonds are present? You guessed it, ionic bonds. So as the solute particles are making room to bond with the solvent particles, ion-ion bonds or ionic bonds are broken. Now between water molecules, there were hydrogen bonds. They had to be broken to create room for incoming solute particles. As sodium ion and chloride ion come in contact with water molecules, now between them, ion dipole attractions are formed. If you recall from intermolecular force chapter, ionic bonds are actually stronger than ion dipole. So why would sodium chloride crystal want to break up ionic bonds which are stronger and form ion dipole bonds which are weaker? The answer lies in increased entropy. Because as sodium chloride is dissolving in water, the entropy is increasing. And this increased entropy counters the fact that the formed bond is weaker than the original bond. So, solution process really has 3 steps in it. First step is separating the solute particles. And this is always endothermic. So there's a positive energy associated. Separating the solvent particles. And this is always endothermic as well. Now the third step, when the solute and solvent come together, could either be exothermic or endothermic. Now this step really determines if overall process will be endo or exothermic. If the third step is highly exothermic, then overall reaction or solution ends up being an exothermic process, spontaneous, readily dissolves. If the third step is slightly exothermic or endothermic, then the overall solution process ends up being endothermic, and that's not spontaneous or does not have great solubility. Now moving on to how do we express solution concentration. So it's oftentimes very important for chemists to know how much of solute is present in a solution or how concentrated is a solution. So we have 4 different ways of expressing the concentration of a solution. One is called mass percent, which is mass of solute over mass of solution, which is mass of solute plus mass of solvent times 100. The second type is mole fraction, which is written as uppercase X, which is moles of A, or written as Na over total moles will be Na plus Nb if there are only 2 components in this solution. Molarity is moles of solute per liters of solution. Please note you don't add this much water. This is the total volume of solution. To make a molar solution, the equipment you use is called a volumetric flask, and you take the weight quantity of solute, you put it in there, and then you dissolve the solute in a little bit of water to give it room to expand due to dissolution of solute in water. And once it has completely dissolved, then you add more water and make up the volume to the mark, so the entire solution's volume is your desired volume. Molality is commonly used in colligative properties. It's written with lowercase m. Please don't confuse between molarity and molality. Molality is lowercase m and molarity is uppercase m. Molality is how many moles of solute are present per kilogram of solvent, not solution, solvent. You will need to memorize all these 4 and be able to apply them in different problems, as you will see in the problem set. Moving on to some of the key terms of vocabulary related to solubility. Solvation means dissolving or creating interactions between solute and solvent. And when the When the solvent is water, we call the process hydration. Crystallization refers to undissolving of solute from the solvent, crystal formation. A saturated solution is the one that has maximum amount of solute that can be dissolved at a given temperature in a given quantity of water. Solubility is how much of solute you need to make a saturated solution of that substance at that given temperature. And obviously you can define unsaturated and supersaturated solutions. What you see here is a solubility curve. In the solubility curve on the y-axis, you have how much or grams of solute per 100 grams of water, and they'll always specify the temperature. At what temperature are you referring the solubility? Because with change in temperature, solubility changes, or if you change the amount of solvent. So in solubility curve, you have temperature on x-axis and how much solute in 100 grams of solvent, which is water in this case, on the y-axis. And any point for a given solute, like sodium nitrate, at any point on the line shows to make a saturated solution at 20 degrees, you need 89 grams of sodium nitrate. Or at 30 degrees, to make a saturated solution of sodium nitrate, you would need about 96 or 97 grams of sodium nitrate. So any point on the line shows a saturated solution. If you have lesser solute than the saturated solution is needed, you have unsaturated solution. And if at that temperature your point lies above the saturation line or solubility curve, that means you have a supersaturated solution. The way to make a supersaturated solution is to dissolve a larger amount of solute into a given quantity of solvent by heating it up and then very gently cooling it so the solution does not realize that it is still holding the extra solute, and that's called a supersaturated solution. At this point, you might want to look at the trends of solubility curves of solids like sodium nitrate, potassium nitrate, ammonium chloride, potassium chloride versus gases like HCl, ammonia, SO2. Pause it here, take a minute, think about what's happening or what's the difference between solid solubility curves versus gases solubility curve, and then come back to me. Yes, as you notice, the solid solubility is increasing with increase in temperature, while gases solubility is decreasing with increase in temperature. And that is why your soda gets flat if you leave it on a hot day in the garage, because all the carbon dioxide that was dissolved in your soda comes out, and you say the soda is flat. Now, this one, you can see the kind of questions that can be asked on solubility curve. They can give you certain amount of solid was dissolved in this much of liquid, and they will give you solubility curve and ask you, is the solution saturated, supersaturated, or unsaturated? So please take a minute with this slide and follow it and see if you'll be able to answer those kind of questions. Moving on, now what are the factors that affect solubility of a substance? So basic principle behind solubility is like dissolves like, meaning a polar substance will dissolve in a polar solvent. The common polar solvent, the most common polar solvent is water, obviously, acetone, CH3, CO, CH3. The CO, the lone pairs on oxygen make it polar. Or ethanol or methanol, C2H5OH. Anytime you have OH, it is, or double bond O, it is polar. So these are polar solvents. The common non-polar solvents are carbon tetrachloride or oil. These are common non-polar solvents. Miscible liquids mix with each other, immiscible liquids that do not mix with each other. There is also Henry's law, which says how much gas can be dissolved in a certain liquid depends upon the gas's partial pressure on the surface of liquid. Hence, when your soda is packed, it is packed under pressure. So a lot more carbon dioxide can be dissolved in the liquid, and you find your drink fizzy and good. So that is Henry's law. And that is why if you notice your soda bottle's plastic is much thicker than the water bottle's plastic, because soda bottles are packed under pressurized air. So the concentration of carbon dioxide in the solution becomes higher. So more carbon dioxide dissolves. Moving on to colligative properties. Colligative properties, so far we talked about intensive, extensive, and all those properties. Colligative properties are the ones that depend exclusively on one thing. They only depend on the number of particles. Doesn't matter whether a substance is a large molecule or a small molecule, or is it polar or it's non-polar. But these properties only exclusively depend on number of solute particles. There are four main colligative properties that we are going to study. First one is called vapor pressure lowering. Second is called boiling point elevation. Third is called freezing point depression. And the fourth one is called osmotic pressure. And you can go on the link here and watch the animation. And I will be showing you the animations, some other animations in a minute. Vapor pressure lowering refers to a phenomenon if you add a non-volatile solute, meaning a solute that will not go in the gas phase, in a pure solvent, then solvent's vapor pressure decreases. This is called, actually we'll call it solution's vapor pressure decreases, or solution's vapor pressure is less than that of pure solvent if you add a non-volatile solute to the pure solvent. Before we can understand vapor pressure lowering, let's understand vapor pressure. So if you have a container with liquid in it, and these dots show the particles of liquid, some high energy particles leave the surface of the liquid and go in the gas phase, and these particles exert a pressure on the surface of liquid, which is called vapor pressure. So the larger the number of particles on the surface of liquid, the greater will be the vapor pressure. Or lesser the intermolecular force between these particles, greater will be the vapor pressure. Now, when you add non-volatile solute to the solvent, two things happen. One, available surface area for these particles to escape becomes lesser. Also, solute-solvent interactions cause greater intermolecular force, so the particles don't escape as much. Hence, the vapor pressure is lowered when you add a non-volatile solute to a pure solvent. This vapor pressure lowering is quantified by Rayau's law, which says that PA is equal to XA times PaO, meaning vapor pressure of solvent, pure solvent, is equal to mole fraction of solvent times vapor pressure, normal vapor pressure of solvent. So this PA is the vapor pressure after adding the non-volatile solute to it, or vapor pressure of solution. This is vapor pressure of solvent, pure solvent, and this is mole fraction of solvent. Now, let's talk about vapor pressure and its connection to intermolecular force. The higher the intermolecular force, the lower will be vapor pressure. Other thing that's important for you to know is the connection between vapor pressure and boiling. So boiling is when the vapor pressure of a substance becomes equal to the atmospheric pressure or external pressure. So if a liquid has higher vapor pressure, it will have a lower boiling point. And if a liquid has lower vapor pressure, it will have a higher boiling point because it will need more heat to bring more particles in the gas phase. So the vapor pressure increases, and then it can become equal to atmospheric pressure, and that is what is boiling. This is vapor pressure of four liquids, is a graph. On y-axis, it shows the vapor pressure. On x-axis, it shows the temperature. And you can note here, as the temperature is increasing, so is the vapor pressure. So with increase in temperature, vapor pressure is increasing for all of these liquids. And can you think, why are there different vapor pressures at the same temperature for different liquids? Yes, it's got something to do with the nature and quality of the intermolecular forces of attraction. The next colligative property is boiling point elevation, Because when you add a non-volatile solute to a pure solvent, its vapor pressure decreases, hence its boiling point increases. That's called boiling point elevation. So solution has a higher boiling point as compared to the solvent at the same uh, uh, for the same substance. So solutions have a higher boiling point. This is called boiling point elevation, and it can be calculated using the formula delta TB, where delta TB is boiling point elevation, is equal to I Kb times m. I is Van 't Hoff's factor, which tells you how many particles does your solute break into. For a molecular compound like sucrose, C12H22O11, Van 't Hoff's factor I will be 1. But for NaCl, I will be 2. Actually, in real life, NaCl's I value will be little less than 2 because of clumping. But for theoretical purposes, we take it as 2. For calcium phosphate, can you guess what the I would be? Yes, it will be 4 because this will break into 4 ions. Kb is called the molar boiling point elevation constant, and for different solvents it has different values. You can only memorize for water, and that's good enough. Similar thing happens for freezing point, but freezing point is lowered as a result of adding a non-volatile solute to a solvent, because now to organize them in a solid you need to remove more heat because of presence of these solute particles in between the solvent particles. And this freezing point depression is given by delta TF is equal to I Kf times m, where delta TF is freezing point depression, I is Van 't Hoff's factor, Kf is molar freezing point depression constant, and m is the molality. Kf for water is 1.86 degrees Celsius kilogram per mole, or degrees Celsius per molal. Osmotic pressure, pi is IMRT, where I is Van 't Hoff's factor, m is molarity, r is gas constant, and T is the temperature. I will be showing you animations after this PowerPoint. The ideal solution is the one that obeys Reol's law at all concentration, but most of the solutions only obey Reol's law at low concentrations. Colloids are substances whose particle size are in between that of a solution and suspension. As a result, colloid particles are suspended in the liquid. They are not large enough to settle down, but they are large enough to scatter light. So what happens if you pass light through a colloidal solution? It lights up the path of the light. This effect is called as Tyndall effect. When light is passed through pure water or solution, you see no lit up path, but here the path is lit up. Now let's talk about phase changes, but before we do that, let's go look over some animations. This is an animation of colligative property. So let's reload it. And let's choose our solvent, which is water, 100 grams, pretty good. Let's choose sucrose first. And let's do a hot water bath, and let's add 3.6 grams of sucrose. And let's see what is the temperature rise. You know that pure water boils at 100 degrees Celsius. And let's see what does this boil at. If boiling point elevation is true, it should be boiling at higher than 100 degrees, which is what you see here. And if we wanted to see its micro level, what's happening because of these non-volatile solute particles, the vapor pressure has lowered. So it takes more heat for more particles to leave the surface so that the vapor pressure becomes equal to atmospheric pressure. This is called boiling point elevation. Now let's try this with sodium chloride, whose Van 't Hoff factor is doubled. For the same amount of sodium chloride, let's see what does it change or increase the boiling point to. So for the same amount of sodium chloride as compared to sucrose, you can see this much larger change in the boiling point or greater boiling point elevation. That's because the Van 't Hoff factor for sodium chloride is 2. So that was boiling point elevation. Now let's look at freezing point depression. So this is water. This one is water. This is ice particles in equilibrium with each other. Now what happens if we add solute? If we add solute, then what happens is solute goes in between and kind of breaks apart the ice particles. So think of its reverse. If you are trying to freeze up water containing some solute, you will need to slow down these particles more or remove more heat to squeeze out these solute particles from in between the water molecules so water can freeze. This is called freezing point depression. And I will come back to this curve in a minute, but I just wanted to address here the dissolving of sodium chloride. So as you can see, you have sodium and chloride, and one by one, each sodium and chloride ion is taken away by water molecules that surround and separate them. This is just dissolution of sodium chloride in water. And this one also shows you that. So let's start it. This is silver chloride that we are dropping in water. And this is a chunk as we see with our naked eye. But if we really apply the molecular scope to it, I like how they do this whole little sci-fi thing here. Now you will see the zoom activated, and now you can see at the particulate level what's going on between Ag and Cl. They are separating out. This is called dissolution or dissolving. And we will come back to this heating cooling curve in a minute. So let's resume with phase changes. So you know solids can melt, liquids can convert to gases, so melting, boiling. Solids can also go directly to gases, that's called sublimation. All the processes going from solid to the right side are endothermic. While all the processes going this way are exothermic. You got to remove the heat for those processes to happen. This is what is called a phase change diagram, which tells you if you take a solid and keep heating it, what happens. So in any phase change diagram, as you see, let's say you started with a solid here. When you give it heat, it melts, changes to liquid here. And while it starts to change to liquid at point B, and all through B and C, the solid is melting or a phase change is happening. During that time, you will not see an increase in temperature. Temperature remains constant. This is because all the heat that you're giving that substance during this time is being used to overcome the intermolecular forces of attraction, which contributes to its potential energy. But because temperature is directly proportional to average kinetic energy, and kinetic energy does not change during phase changes, hence you see the flat portions or no change in temperature during a phase change, even though you're giving it heat. As soon as all of the solid changes to liquid, then the temperature starts rising again till the liquid to gas phase change starts happening or boiling starts happening. You'll also notice that the boiling flat curve is much larger than the melting one. That's because when you're boiling or changing a liquid to gas phase, you are breaking almost all intermolecular forces versus some in going from solid to liquid. Now I'm going to show you the interactive to explain this further. So let's look at a heating cooling curve of water molecule. Actually, we start with negative 15 degrees ice, and as you heat it up, its temperature rises till you hit 0 degrees. At 0 degrees, ice starts to melt, and as you give it more heat, it just continues to melt till all the ice has melted to water. Then its temperature begins to rise again till all that liquid water starts changing and has changed to gas during the flat portion. And then if you continue heating, then you get superheated gas. Okay, so this is gas particles. Now you have superheated gas. Now, how do you calculate amount of heat given at each of these? In the non-flat portions, you use Q is mc delta T because you have a temperature change happening. M is the mass of substance. C is the specific heat, which it's a good idea to memorize for water or ice. And for the flat portion, you calculate it Q as mass times heat of fusion, which is melting, or heat of vaporization. And just by multiplying, you can get your values. Now on to the last part of this podcast, which deals with the phase diagrams. Phase diagrams tell you what are the different temperature pressure conditions, and under those conditions, in what phase does a substance exist. Phase diagram is almost like a fingerprint, so you can identify a substance by looking at its phase diagram. Every phase diagram has 3 lines separating the boundaries of solid, liquid, and gas. The first one is solid phase, second is liquid, third one is gas. And generally you notice as the temperature increases, or generally as the temperature increases and pressure increases, you will see that the substance is moving from solid to liquid to gas phase. With increase in pressure, the solid phase is becoming more prominent because as you increase the pressure, it compacts the phase or goes towards a higher density phase. So as the pressure is increased in most substances, solid phase becomes more pronounced because that is more dense. But that's not the case for water. You know, for water, the liquid phase is more dense than the solid phase. So as the pressure is increased, the liquid phase becomes more prominent and solid phase becomes less prominent. This is called a negative solid liquid interface of water. This is a very peculiar thing that happens in water, and this is how water's phase diagram is different than most other substances because in water the liquid phase is more dense than the solid. Coming back to the phase diagram, where all these 3 phase lines meet, we call that point as a triple point. Under this condition of pressure and temperature, solid, liquid, and gas phase of that substance can exist in equilibrium. So for carbon dioxide, that is 5.11 atm and negative 56.4 degrees Celsius. So no wonder at 1 atm and let's say room temperature around 25 degrees Celsius, carbon dioxide can only exist as gas. Hence, we see that our dry ice becomes smoky and sublimes at room conditions. For water, the triple point exists at 0 degrees Celsius, little above 0 degrees, but you need about 5 atm pressure for all these 3 phases to exist. 4.58 torrs, sorry, not 5 atm, 4.58 torrs of pressure for all these 3 phases to coexist or for triple point. At 1 atm, which is our room pressure, and 25 degrees Celsius, you can have either the solid or the liquid phase of water. For getting it to gas phase, you will really need to heat it up to a higher temperature. So that is phase diagram. And with that, this podcast comes to an end. Thank you for listening.